Okay. Right at the point where we start on two-dimensional elasticity, where we are going to reduce this 15 equations, 15 governing equations in 15 variables into a smaller set. Uh, when we do that, it is important to realize that there are no two-dimensional or three-dimensional bodies in nature, or everything in nature is three-dimensional. But uh, in in order to make the equations tractable, some standard assumptions are used about the geometry and the loading on a body in order to reduce the number of variables and equations that we need to handle, and thereby sometimes, not always though, making the problem solvable in a closed form. So actually three of these situations we are going to discuss. The first one we are going to discuss is known as a plane strain assumption, which is applied to a body which is geometrically very long in one direction. So we have taken that direction to be x3, it can be any others. So it's very long in this direction compared to its dimensions in the x1, x2 plane. So compared to the cross-sectional dimensions, the length dimension in the x3 direction is very, very large. Uh, on top of that, if the loading on this three-dimensional body is such that the loading does not vary with the x3 dimension, and the body is so long that when it deforms, this cross section suffers no out of plane deformation. That means there is no displacement of this cross section in the x3 direction, or in other words, the plane cross section perpendicular to the x3 axis remains plane even after deformation. In that case, this qualifies as what is known as a plane strain situation. So let me repeat that there are two conditions to plane strain. One is a geometric condition. The body has to be very long in one direction compared to its dimensions in the other two directions. That's the first geometric requirement. And the second requirement is in the terms of load, uh, in the sense that the loading should not vary in the x3 direction. In the long direction, the loading should not have any variation, and plane cross sections perpendicular to the loading direction should always remain plane. If this is satisfied, it basically means that if I take a cross section, if I take this cross section, or if I take a cross section somewhere here, there is nothing really to choose between the two. Both are completely equivalent because things do not vary in the x3 direction. Things do not vary in this direction. Therefore, I can take a cross section anywhere, and that cross section will be as representative a cross section as any other. Okay, so in this situation, the problem can be reduced to one which works only on the x1, x2 plane. Okay, so uh, the basic assumptions, therefore, basic assumptions in plane strain are on displacements, where the displacement component u1 is a function of x1 and x2, u2 is a function of x1 and x2, and u3 is identically always equal to 0 because plane cross sections remain plane. On top of that, all quantities, when their derivatives are taken with respect to x3, give you 0 because things do not vary in the 3 direction. Okay, now with these assumptions in place, we can immediately see that there's a significant amount of simplification that happens to the equations governing the problem of linear elasticity. So for example, in the strain displacement relations, which is, we all know by now, is epsilon ij equal to half ui comma j plus uj comma I. Think of epsilon, let's say 2, 3, which would be half del u2 del x3 plus del u3 del x2. Now del x3 is 0 everywhere, so this is 0. u3 is 0 everywhere, so this is 0 as well. So epsilon 2 3 will be identically equal to 0. If you look at epsilon 3 3, it would be del u3 del x3, which will also be equal to 0. If you look at epsilon 3 1, it will be half u3 comma 1 plus 1 comma 3, which will also be equal to 0. So the only non-zero strains will be epsilon 1 1, which is del u1 del x1, which will not be 0 because of this relation. Epsilon 2 2, epsilon 2 2, which will not be 0 because of this one, and epsilon 1 2. So these three would be the only non-zero components of strain. And as you can imagine, if I take a small pillbox here, I can draw epsilon 1 1, epsilon 2 2, and epsilon 1 2. All this I can draw only on the x1 x2 plane, hence the name plane strain. All the strain components can be drawn on the x1 x2 plane when x3 is the long axis. Okay, this is the first simplification. The six strain displacement relations reduced to just three in epsilon 1 1, epsilon 2 2, and epsilon 1 2. The rest of the strain components are equal to 0. Okay, so these are the only non-zero strain components 1 1, 2 2, and 1 2. Okay, now let us look at the equilibrium equation, and especially let's look at the equilibrium equation. Remember, the equilibrium equation is sigma ij comma j plus bi equal to 0. There can be no loading in the three directions. So for 3, this is 3j comma j plus b3 equal to 0. b3 has to be equal to 0 because the body force cannot have an out of plane component. Nothing varies in the z direction, remember, x3 direction. So, and out of this sigma 3j comma j, you will have sigma 31 x1 plus sigma 32 x2 and sigma 33 x3, and you will see that this is 0 because del x3 of everything is equal to 0. In the linear in the linear elastic isotropic case, if sigma ij is equal to 2 mu epsilon ij for shear strains when I not equal to j. So if epsilon 13 is equal to 0, so is sigma 13, and epsilon 23 is equal to 0, so is sigma 23, which makes this equal to 0 and this equal to 0, which means the third equation of equilibrium for I equal to 3 is identically equal to 0, is trivially equal to 0, and need not be satisfied separately by the assumptions of the problem that you have made. The third one is already equal to 0. In the first and the second equations, so the first equation for I equal to 1, let's write that 1 1 1 2, and then you have a term sigma 1 3 x3. So this term is also equal to 0, and here also you will have a term sigma 2 3 x3, which will also be equal to 0 for the reasons that we have just discussed. So not only do we have just two pertinent equations of equilibrium, we also have only two terms, two derivative terms, stress derivative terms in each of them instead of three. So these are the two equations of equilibrium. So we have three equations for strain displacement, two equations for equilibrium, and the constitutive equations also will be further reduced, and that's what we are going to see now. So in the constitutive equations, remember the constitutive equations in general are sigma ij So this is your constitutive equation, out of which we know epsilon 33, epsilon 23, epsilon 13 are equal to 0. So When you write sigma 1 1, for example, when you write sigma 1 1, you have lambda, so that's epsilon kk, plus 2 mu epsilon 1 1, out of which this is going to be 0. So you will have lambda epsilon 1 1, epsilon 2 2, and 2 mu epsilon 1 1. Similarly for sigma 2 2. For sigma 1 2, you have delta ij equal to 0. So you have 2 mu epsilon 1 2. The equations, as I said, for sigma 1 3 and sigma 2 3 are identically equal to 0. We don't need to consider them. The important thing to note is sigma 3 3. So sigma 3 3, if you look from here, will be lambda epsilon kk plus 2 mu epsilon 3 3, and now this is equal to 0 because epsilon 3 3 is 0, but this is there. So this will be equal to lambda epsilon 1 1 plus epsilon 2 2. So you can either leave it at that, leave it as epsilon 1 1 plus epsilon 2 2, or you can use these two equations to solve for epsilon 1 1 and epsilon 2 2 in terms of sigma 1 1 and sigma 2 2, then convert lambda and mu to terms of e and nu, and you will find that uh, sigma 3 3 comes out to be nu times sigma 1 1 plus sigma 2 2. So both of these are equivalent relations, one in terms of strain, one in terms of stress. What we see from this last relation is that sigma 3 3 is not equal to 0. Sigma 3 3 is not equal to 0 in plane strain. So sometimes I will use this for plane strain. Sigma 3 3 is not equal to 0 in plane strain. However, it is not also independent, because sigma 3 3 can be found once you have found sigma 1 1 and sigma 2 2. So just like in the strains, you need to find sigma 1 1, sigma 2 2, and sigma 1 2. But you have to remember in plane strain that sigma 3 3 is not equal to, not identically equal to 0. It is dependent on sigma 1 1 and sigma 2 2. So as it happens in plane strain, you cannot draw the stresses all in the xy plane or the x1 x2 plane. So if you try to draw the stresses now, so take a pillbox. This is your sigma 1 1, this is your sigma 2 2, this is sigma 1 2, and you have a out of plane stress sigma 3 3 as well. So the stresses cannot be all drawn on the x1 x2 plane, but the sigma 3 3 is not independent, and you basically have to solve for 1 1 2 2 and 1 2. Okay, so this is plane strain, and in plane strain, the Navier's equations also reduce to only these two. So del square ui is now, for I equal to 3, del square u3 is now del square u3 del x1 plus del square u3 del x2 plus del square u3 del x3. So this is identically equal to 0. And then del x3 of del u1 del x1 plus del u2 del x2 plus del u3 del x3 is also equal to 0, because del x3 of anything is equal to 0. So the third Navier's equation also becomes identically satisfied, trivially satisfied, as 0 equal to 0. Okay, so so you are left with only two Navier's equations, and in these Navier's equations, the terms involving del x3 are absent. So the terms involving del x3 here are absent. Terms involving del x3 here are also absent, because they are identically equal to 0. You don't have B3, so the third equation, B3 also doesn't appear. So these are the two Navier's equations, and if you go back to your strain compatibility equations, you will see that because only strains are epsilon 1 1, epsilon 2 2, and epsilon 1 2, out of the six compatibility equations, only this remains relevant. So this is the only compatibility equation that we need to satisfy out of the six that we have. So we now have just two displacements, U1, U2, three strains, four stresses, out of which this is not dependent. This is dependent on sigma 1 1 and sigma 2 2. So basically you have to find three stresses. So you have altogether 8 variables and 8 equations to solve. Two equilibrium equations, three constitutive equations, and three strain displacement relations. There are four constitutive equations, you will say, but again this constitutive equation you don't need to really solve because the right hand side is a function of the other two. So you have basically three constitutive equations, 8 equations in 8 unknowns, which is theoretically at least possible to solve. Now another standard, oh by the way, boundary conditions. So the boundary conditions for a plane strain problem will also get significantly reduced. So now since you are solving the problem on the x1 x2 plane, so this is your cross section of that long body, and this is x1, this is x2. Since you are solving it on the x1 x2 plane, the normal at a point n will have only components n1 and n2, and n3 will be equal to 0. By definition, the traction also, applied tractions, cannot have components T3. So everything has to be in the x1 x2 plane. Every loading has to be in the x1 x2 plane, so it will be T1 bar, T2 bar, and 0. Therefore the Cauchy relations will now reduce to just this. There is, remember, the Cauchy relation is Ti bar equal to sigma Ji Nj, and since Nj can be N1, N2, 0, so the N3 term will not be there. There would be no equation for T3 because the T3 bar equation, so T3 bar is sigma 1, 3, N1 plus sigma 2, 3, N2 plus sigma 3, 3, N3, and N3 is equal to 0, sigma 2, 3 and sigma 1, 3 are 0, so T3 is equal to 0 also. So 0 equal to 0, the third equation is a trivial one, and you are left with only these two on del Vt. On del Vu, you can have U1 specified as U1 bar, U2 specified as U2 bar, but then also U1 bar and U2 bar have to be functions of x1 and x2 in both cases. They cannot be functions of x3. If this all happens if you have plane strain situations in place. Okay. Now the other standard situation that arises is one of plane stress. So it's called plane stress, and this happens in cases where the dimensions of the body in the x1 x2 plane, let's say, is much larger than the dimension in the x3 direction. So for example, for a large thin plate lying in the x1 x2 plane, plane stress situations would apply. Now plane stress situations also follow from, plane stress situations are approximations which follow from the Cauchy relation. Now see that this plane has to be, this plane as well as the plane behind has to be traction free. This has to be a traction free plane. The loading has to be completely in the x1 x2 plane. So this plane is traction free, which means that if I take the normal to this plane, if I take the normal to this plane, then if I take the normal to this plane, the normal is 0, 0, 1 for this plane. Now traction on this is 0. So T bar on this is equal to 0, which means T1 bar, T2 bar, and T3 bar is equal to 0. So right next to this point, if the Cauchy relations are satisfied, you must have T1 bar equal to sigma 1 1 n1 plus sigma 1 2 n2 plus sigma 1 3 n3. Now, for this plane, only n3 is 1, so this is 0, this is 0, and T1 bar is also equal to 0, which implies that sigma 1 3 right next to the point where you're taking the normal is equal to 0. If you work it out, you will see that sigma 2 3 will also be equal to 0, that you can work out from the fact that T2 bar equal to 0, and then sigma 3 3 is also equal to 0, which you can work out from the fact that T3 bar equal to 0. So these three will be equal to 0 at x3 equal to t. If you look at the plane behind, that is x3 equal to minus t, you will see that that's also a traction free plane. There also T1 bar, T2 bar, T3 bar is equal to 0, but the normal to the plane is 0 0 minus 1. So if you put 0 0 minus 1 at the normals as the normals on a traction free plane, you would come to the same conclusion as here, that sigma 1 3 sigma 2 3 sigma 3 3 are equal to 0 on x equal to plus minus t. On the front face as well as the back face, x3 is equal to 0. Now the idea goes that sigma 1 3 sigma 2 3 sigma 3 3 are continuous well behaved functions. So if they are continuous functions, then at x3 equal to plus t, they have to be 0. Then they can vary away from 0, but at x equal to minus t, again they have to become 0. So since 2t is a very small number, they have to be continuous functions which start from 0 and end up 0 very quickly. So as a first engineering approximation for plane stress case, we can take sigma 1 3, sigma 2 3, and sigma 3 3 to be 0 everywhere. Okay, so if we take them to be 0 everywhere, the stresses that can be non-zero are sigma 1 1, sigma 2 2, and sigma 1 2. Okay, and now you can see that the stresses, this is sigma 1 1, sigma 2 2, and sigma 1 2. The stresses can now be drawn on the x1 x2 plane. We still don't know about the strains, but the stresses can be drawn on the x1 x2 plane. So this is the basic assumption of plane stress. It arises from the fact that these planes, the x3 planes, are traction free, and the thickness in the x3 direction is very, very small. Now, I'm not going to work out this in as much of a detail as I did for plane strain, but we can again show that now epsilon alpha beta, where we are using these Greek symbols, Greek subscripts, which go from 1 to 2, not from 1 to 3. So epsilon alpha beta, this should be epsilon alpha beta, not alpha comma beta. So epsilon alpha beta is equal to half u alpha comma beta, beta comma alpha. So this takes the values 1 1 1 2 and 2 2 only. So 3 does not arise here. So the strain displacement relations can be expressed in this form. Again, the equilibrium equation can be expressed in this form, which is same as what we did for the plane strain case. So if you go back to the plane strain case, you would see that these were the equilibrium equations. These are the strain displacement relations, and they are basically exactly same as what we have in plane stress here. The difference arises in the constitutive equation, and I don't derive this in detail. This is the constitutive equation for the general case, and then you can show for the plane strain and the plane stress case that the constitutive equation can now be expressed in this form. Constitutive equation can now be expressed in this form, where the only thing that changes is kappa, where kappa is this for plane strain and this for plane stress. So once you replace the value of kappa, plane strain and plane stress problems can be cast in the same constitutive equation, which is this. And strain compatibility is governed by only one of the 6 equations, and that is same for plane strain and plane stress. So please, from here, please try to derive this for plane strain as well as plane stress. And you need to remember this. This is a very, very important relation that we'll make use of. Okay, so plane strain and plane stress are similar, but there are important differences. So in plane strain, the strains can be drawn on the x1, x2 plane completely, but the stresses cannot be because there's a sigma 3, 3. In plane strain, if you work it out, you will see that, in plane stress, you will see that the stresses can be drawn on the x1, x2 plane, but epsilon 3, 3 is not equal to 0, though sigma 3, 3 is equal to 0. And epsilon 3, 3, like in the plane strain case, is also dependent on epsilon 1, 1 and epsilon 2, 2. In fact, it is, I think, minus nu epsilon 1, 1 plus epsilon 2, 2. So it's not independent. It's dependent on epsilon 1, 1 and epsilon 2, 2. But in plane stress, the strains are not, out of plane strains are not all 0. In plane strain, the out of plane stresses are not all 0. Okay, so this is an important distinction you have to remember, and you have to also remember the geometric and the loading conditions that qualify a 3-dimensional problem to be treated as either a plane strain problem or a plane stress problem. If you can do that, then you have the advantage of having reduced the number of equations significantly. But you have to remember that there is a difference in the constitutive equation. In the constitutive equation, there's a difference that arises because of the difference in the kappa. So plane strain and plane stress constitutive equations are slightly different. Their stress and strain states are, of course, different. But in both cases, all we have to solve for are the in-plane stresses and strains. Once we do that, the out-of-plane strains or stresses, as the case may be, can be derived as a post-processing exercise. The third third standard situation, which actually simplifies much more than both the plane strain and plane stress case, is the anti-plane shear case. The anti-plane shear is something like this. Think of a cross-section of a body. So this is in the x1, x2 plane. Okay, and think of the displacement field at a point, and the displacements are such that we can assume that u1 and u2, the in-plane components, are both equal to 0. But the out-of-plane component is either coming out of the plane or at some points going into the plane. So this is like either coming out towards you or going in away from you into perpendicular to the plane of the slide. So in that case, u1 and u2 is always equal to 0, and u3 is a function of position on this plane. That is, u3 is a function of x1 and x2, but u3 is the only component of displacement that is present in the problem, that is significant in the problem, and u3 is the out of plane displacement, which can be either into the slide or out of the slide. That's all. And u3 will be a function of x1 and x2. In fact, we call it a special function w. So u3 is w of x1, x2. u1, u2 are identically equal to 0. If this is the situation, then it's easy to prove that, for example, epsilon 1, 2 is half u1 comma 2 plus u2 comma 1 is identically equal to 0, and the only epsilon 3 3, let's say, is del u3 del x3, but u3 is not a function of x3, so this is also equal to 0. So the only non-zero components of strain would turn out to be epsilon 1 3. Why? Because epsilon 1 3 is half of u1 comma 3 plus 3 comma 1. 1 comma 3 is equal to 0 because u1 is 0 identically, but 3 comma 1 is not equal to 0, and 3 comma 1 is actually equal to del w del x1. So epsilon 1 3 is half del w del x1. Similarly, epsilon 2 3 is half del w del x2. Now, we know for isotropic linear elastic materials, if uh, shear strains cause shear stresses and shear stresses cause shear strains, shear stresses and strains have no truck with normal stresses and strains. So if epsilon 1 3 is there, sigma 1 3 is there as well. So sigma 1 3 is 2 mu times epsilon 1 3, and sigma 2 3 is 2 mu times sigma 2 3. That means sigma 1 3 is mu times del u del w del x1, and sigma 2 3 is mu times del w del x2. Now plug this into the equilibrium equation, and in this case the only relevant equilibrium equation would be the three wala equation, which would give you sigma 3 1 x1 plus sigma 3 2 x2 plus sigma 3 3 x3 plus b3 equal to 0. But we know that this is equal to 0 because sigma 3 3 is equal to 0. And then this sigma 3 1 is mu times del w del x1. So del x1 of that would lead to mu times del square w del x1 square. Similarly, del x2 of sigma 3 2 would lead to sigma 3 2 would lead to this. And when you put that together, this is what you will get. This is what you will get. In fact, when body forces are absent, when B3 is also equal to 0, so if B3 is also equal to 0, then what you have is where this del square W is simply del square W del x1 square plus del square W del x2 square equal to 0. So this is what you will have to solve. So you will have to basically find a function which satisfies the harmonic equation, and then if you can find a function which satisfies the harmonic equation and the boundary conditions given for the problem, then you have found the solution. Remember, for a linear elasticity problem, the solutions are always unique. So if you can find one solution, even by guessing, if you can find a solution which satisfies the governing equations and the boundary conditions, then you are done, then you have found the solution. So what this equation tells you that if you know of solutions of harmonic equation, you should look for only in the set that satisfies harmonic equations. So if you know such solutions, then you can use them to find a solution to antiplane shear problems. So antiplane shear problems um, are governed by the harmonic equation, where the function in the harmonic equation is the displacement in the third direction. Plane stress and plane strain problems are what we will now turn to, and we will first try to solve plane stress and plane strain problems, which will lead to a equation somewhat more complicated than the harmonic. The antiplane shear problem is the easiest of the lot because it leads to the harmonic equation, for which there are a lot of known solutions. The plane stress and plane strain will lead to something slightly more complicated, which will require some more skills, some more knowledge to solve. Let's stop here.